Welcome back. We have seen that step functions create problems with their sudden jumps. What we need is smooth S-shaped curve that gradually transitions from 0 to 1. But to build that perfect curve, we need to understand two special mathematical functions, exponentials and logarithmics. This might sound intimidating, but they are actually everywhere in nature and technology.
Woo! My $10 is gonna make me rich!
Homer, that's how exponential functions work. They start small but grow rapidly.
Today we will explore these functions visually and intuitively, setting up the foundation for the sigmoid function that solves our perceptron problem. Let's start with the exponential function fx equals to e of x. The base e is a special mathematical constant, approximately 2.718. Don't worry about memorizing it, just know it creates very smooth natural curves. Look at this f of x equals to e to the power x. When x is equals to 0, e to the power 0 equals to 1. When x is equals to 1, e to the power 1 equals to 2.7. When x is equals to 2, e to the power 2 will give you almost 7.4. And when x is equals to 3, e to the power 3 will give you almost 20.1. Notice three important things, always positive. E to the power x never goes below 0. Smooth everywhere. No sudden jumps or corner. Grows rapidly. Small increase in x create large increases in output. Exponentials appear everywhere. Population growth, compound interest, radioactive decay, viral spread, like a social media post that goes viral. This smoothness and rapid growth make exponentials perfect building blocks for our neural network functions. Now let's look at what happens with negative inputs. F of x e to the power minus of x. This creates a completely different behavior. When x is equals to 0, e to the power minus 0 will give you e to the power 0 equals to 1. When x is equals to 1, e to the power of minus 1 will give you almost 0.37. And when x is equals to 2, e to the power minus of 2 will give you almost equals to 0.14. And when x is equals to 3, e to the power of minus 3 will give you almost 0.05. As x gets larger, e to the power of minus x gets closer and closer to 0, but never quite reaches it. This gives us exactly what we need. Smooth continuous curve, always positive, never negative. Approaches 0 for large inputs, equals to 1 when input is 0. Here's a hint of where we are going. What if we could create a function that approaches 0 for very negative inputs, approaches 1 for very positive inputs, smooth transitions between them? The exponential function will be our key ingredient. Now let's meet the logarithm, the inverse of the exponential function. If y is equals to e to the power x, then x is equals to natural log of y. The natural logarithm ln undoes what the exponential does, that is ln of e to the power 3 equals to 3. ln of e to the power of minus 2 will be equals to minus of 2, and ln of 1 will be 0 because e to the power 0 equals to 1. Look at the function f of x equals to natural log of x, only defined for positive x. You can't take the log of negative numbers, passes through the point 1 to 0, grows slowly, much slower than exponentials, has a vertical asymptote at x is equals to 0. Logarithm appears in measuring earthquake magnitude, Richter scale, sound levels, decibels, pH levels in chemistry, information theory and data compression. Like exponentials, logarithms are incredibly smooth. They have derivatives everywhere, which means we can use them for learning algorithms. So why do exponentials and logarithms matter for machine learning? Well, mainly because of these three reasons. Essential for gradient based learning, that is smooth derivatives. Output stays in a reasonable ranges, that is bounded behavior. And when combined cleverly, we get natural S-shapes. Here's the sneak peek at our destination. What if we create a function f of x equals to 1 by 1 plus e to the power of minus x. E to the power of minus x, our negative exponential, goes to 0 for large x. 1 plus e to the power of minus x, always greater than 1. 1 by 1 plus e to the power of minus x, a fraction that's always between 0 and 1. So let's see the behavior. Mainly we have three cases. For large positive x, e to the power of minus x will always be 0. So f of x will almost be 1 by 1 plus 0, that is 1. For large negative x, e to the power of minus x will almost be infinity, so f of x will almost be 1 by 1 plus infinity, that is 0. And for the third case, for x equals to 0, e to the power of minus 0 equals to 1, so f of x equals to 1 by 1 plus 1, that will be half, that is 0.5. So this creates a smooth S-shaped curve that output probabilities from 0 to 1, has smooth gradients everywhere, transitions gradually, not suddenly. This is the sigmoid function, our solution to the perceptron problem. One quick practical note: exponentials can create very large or very small numbers. For example, e to the power of 100 is astronomically large and e to the power of minus 100 is incredibly tiny. In practice, we use computational tricks to keep numbers in reasonable ranges. Programming languages and neural network libraries handle this automatically, but it's good to know why sometimes you see terms like numerical stability in machine learning papers. The beautiful thing about exponentials and logarithms is that they give us smooth, well-behaved functions that are easy to differentiate, crucial for learning, stay bounded in reasonable ranges, create natural probability like outputs. These properties make them perfect for neural networks. Let's recap what we have learned. Exponential functions e to the power of x grow smoothly and rapidly. Negative exponentials e to the power of minus x decay smoothly towards 0. Logarithms are the inverse of exponentials. These functions are incredibly smooth, perfect for learning algorithms. In our next video, we will combine these insights to create the sigmoid function, the smooth S-shaped curve that solves our perceptron problem. We will see exactly how the function 1 by 1 plus e to the power of minus x creates the perfect probability output for neural networks. Thanks for watching this video, and I will see you in the next video where we will finally get our smooth learnable activation function. Bye.